Greetings everyone. I am Angel Bosel, student of Colgate International College, and for today's presentation, my topic is orbital dynamics of hypothetical exomoons around a Jupiter-type exoplanet Laligrass. For this project, Ayush Gautam is my collaborator, Suman Sattal and Sri Krishna Batra are my supervisors. Moving to the introduction, since the recognition of first explored exoplanet named 51 Pegasi b, till today there are more than 4,000 of these explored. And during this going on, in 2007, there was a system found consisting of a Jupiter-type exoplanet HT100777b orbiting around a star HT100777. These were later on named as Laligrass and Sagarmatha by IAU's campaign Name Extroverts, which was organized here in Nepal by NASU in 2019. These were Nepali names, so we were so much convinced to study more about the system. And hence, we are here studying the feasibility of moon size and Earth size exomoons around the exoplanet Laligrass, considering this whole system as restricted three-body problem. So, to the core discipline within the space exploration. Orbital dynamics is the application of ballistics and celestial mechanics to the practical problems concerning the motion of the spacecraft. And these 6 parameters shown in the screen are known as orbital elements. These are very much important in order to identify an orbit uniquely. We know about eccentricity, semi-major axis, and inclination, so I'm going to jump right to the longitude of the ascending node. This is the angle between reference direction and the ascending node, which is the region where two of the planes, plane of reference and the orbital plane, pass through each other. Next argument of periapsis is the angle between the node and the blue line shown in the figure, which represents the closest distance that a satellite can approach to its primary body. The last one is the true anomaly. This defines the position of the body in its orbit at a certain time. In orbital mechanics, to find the equation of motion of the bodies, Newton's law of gravitation plays significant amount of role. And in two-body problem, as shown in the figure, there are two bodies influencing each other gravitationally, and we can find out the position vector of its center of mass using the first equation, which is nothing but Newton's law of gravitation, and the mathematical tool, which is differential calculus. We can also find the relative motion by using these equations. Next one is restricted three-body problem. In this problem, there are three bodies as shown in the figure, and two of them move in circular coplanar orbits about their common center of mass. And there is a third body with negligible mass, which is unable to have any sort of influences in the motion of these two bigger bodies. So this system is known as restricted three-body problem because it is concerned with the motion of this third body, which is restricted to have any sort of influences to other two bigger bodies. We can find out the equation of motion of this third body by using inverse square law and the reduced mass of two bigger bodies. Equation 5 here is nothing but the conversion of the equation of motion into the synodic coordinate. And u here is the scalar function of the equation of motion. Now, Jacobi integral. This is very much important in this system because it is the only conserved physical quantity. This is also known as motion constant, and it can be expressed in terms of position and velocity, which is very much useful to find out the zero velocity surface in the space. This region is the region in the space where no body can move. So this can also lead to the derivation of Hill's radius, hence it is very much important. So for a body to be stable, it needs to be located in between the Hill's sphere and the Rogers limit. Hill's sphere is the region in which the primary body dominates the attraction of the satellite. And outside the sphere, it has no any sort of gravitational influence to its satellite. If somehow the satellite escapes from the primary body's Hill's sphere, it will get attracted by a bigger body. For instance, Moon is revolving around the Earth because it is inside the Hill's sphere of the Earth. If somehow it gets skipped from there, it will get attracted by the sun and it will be inside the sun's Hill's sphere. And instead of revolving around the Earth, it starts revolving around the sun. So for a satellite to be stable and revolving around its own primary body, it needs to be inside the Hill's sphere of its own primary body. This is the formula for Hill's radius, which is the radius of the Hill's sphere. And for our exomoon, it is equal to 0.04368 astronomical units. In contrast, Ross's limit is the closest distance for satellite to approach its planet without experiencing tidal forces. So, as shown in the figure, if satellite gets closer to the Ross's limit, planet's tidal forces start distorting the shape. And if somehow it gets inside the Ross's limit, it starts facing the disintegration. So the fun fact here is the rings of the Saturn lie on the Ross's limit of the Saturn. So it is possible that the particles of the rings are probably the disintegrated bodies of a demolished moon. Here, D represents the value of Ross's limit, and the formula is shown in the screen. So, application of chaotic indicator magnamap. Firstly, chaotic region is the region which is undeterministic, or in simple words, here anybody is unstable. Second, quasi-periodic regions, in the other hand, is the region where body's characteristics show irregular periodicity. Now, the numerical tools used to distinguish between these regions are known as chaotic indicators, and magnamap is one of them. Magnamap technically provides the magnitude of exponential divergence of orbits, and we choose magnamap over other indicators because it is easier for us to visually distinguish between stable and unstable regions. And here is the magnamap of moon-sized exomoon for 10,000 years. The color bar on its right shows the value of magno from red, which is equals to 4, which is the least stable, to green, which is equals to 2, to the most stable region. X-axis here is the semi-major axis and Y is the eccentricity. And the green shade here shows the best orbital configuration for a stable exomoon. Within the green shade of the magnamap, we chose 5 different sets of orbital elements and tested the stability of the exomoon. Now, as we know that semi-major axis is responsible for the shape of the orbit, we first plotted the semi-major axis, and the result is shown in the screen. So this graph here is the orbital positions of the exomoon from perspective of Laligoras for 2 million years, and we have supposed Laligoras in 0, 0 coordinate. So from here we can conclude that the shape of the orbit is sound. Similarly, we plotted the variation of semi-major axis and eccentricity with time. In the first graph, the fluctuations are representatives of the disturbances faced by the exomoon. So these are probably because of the gravitational influences other than that of the Laligoras, which in our system is probably because of the Sagarmatha to the exomoon. We can also notice a pattern where the semi-major axis with higher values shows more fluctuations. Now this is probably because the farther the semi-major axis is from the Hill's radius, it is more safer. And similarly, eccentricity with lesser value is more stable because the value near to 0 is more circular. We repeated the whole process for Earth-sized exomoon. The magnamap of Earth-sized exomoon, as we can see, is similar to that of the previous one. And from the same way, we traced the orbital positions of the exomoon, but for 10 million years, and this is the reason why the outer orbits of this graph is comparatively denser than that of the moon-sized exomoon. This graph of Earth-sized exomoon shows the same result as that of the moon-sized exomoon. As conclusion, we can say that there can be stable exomoons having certain orbital elements selected on the basis of perturbations they faced for significant amount of time. This can be shown from the graph we plotted, and we can say that best configuration for stable exomoon is semi-major axis near to 0.010 to 0.012 astronomical units and eccentricity less than 0.02. This is the list of my references. So thank you so much, and if there are any questions for me to answer, I would feel very honored.
Thank you, Angel. Now, question.
So, meanwhile, can I say something?
Hello.
Hello, can I say something? Yeah, I forgot to mention to you, friends. They were so kind to has with us. They gave us access to FCC to my collaborator Irish Burton. So I want to thank National University for that opportunity. Yeah, I forgot to mention in the presentation that's all.
Nah. So, if not anyone, I will.
Maybe I can ask one question. Like, let's think about a thought experiment that let me pull our moon within the road's limit that you just talked. Can we make the Earth with a ring like the Saturn has?
Okay, for that we need to push moon with some kind of external influences to be near to the Roche's limit because moon outside the Roche's limit is only with its own gravitational force. It is not affected by any other influences. So it needs to be first influenced by other sort of forces to be like near to Roche's limit, and then it can be like demolished.
Thank you. That's
Thank,
enough.
Thank you for your question.
any other question? No. Okay. Thanks, Angel, for a really wonderful talk. So
Thank you so much for this.
okay. So our next topic is comparative study of GPS take and IRI 2016 take total during total solar eclipse of 22nd July 2009 over Nepal, and this is going to be presented by Agrima Nana Shrestha. She's from Amritsar campus, Nepal. So here we go.
Good morning and namaskar, everybody, all the respected professors, teachers, and all dear participants. I am Agrima Nana Shrestha from Amrit campus, MSc third semester, and I am here to present our research work entitled Comparative Study of GPS TEC and IRA 2016 TEC during the total solar eclipse of 22 July 2009 over Nepal under the supervision of Dr. Inka Migoya Oru. And this is the content of my presentation. So moving to the introduction at first. Let's begin with the Earth's atmosphere. The Earth's atmosphere is the layer 1600 km above the Earth's surface. In figure 1.1, we see the different layers of the atmosphere as troposphere, stratosphere, mesosphere, thermosphere, and exosphere based on the temperature distribution, with variation of temperature, electron density, height, and conductivity. The region extending from mesosphere to thermosphere is called ionosphere. So for it, let's move to the other. Ionosphere is highly variable in space and time, such as seasonal, diurnal, and the sun-spot cycle with geographical location and solar-related ionospheric disturbances, and is mainly divided into four layers: D region, E region, F1 region, and F2 region based on plasma density and the altitude as shown in figure 1.2. And the main parameter that directly affect the radio signal of the ionosphere is TEC. So what is TEC? TEC is the total number of electrons within an area of 1 square meter cross section along the integrated path from satellite to the receiver. And global positioning system is used to calculate the TEC value to display the ionospheric errors and to correct those errors. TEC is highly controlled by the solar activity, so it is obtained to be maximum in the equatorial region. Here we have used GPS and the IRA 2016 model to calculate the TEC value. International Reference Ionosphere is a joint undertaking by Committee on Space Research and International Union of Radio Science with the goal of developing and improving the international standard for the parameter in Earth's ionosphere for the radio propagation energy. And IRA 2016 is the improved version with two new models for active peak electron density, height, and the ion composition at low and high solar activity. And here we are going to see the TEC variation during the total solar eclipse. So what is total solar eclipse? Total solar eclipse occurs when new moon occurs between Sun and Earth and cascades amla on Earth, due to which the photochemical activities in the ionosphere decreases rapidly, which affects the Earth's environment with huge disturbances of the solar radiation. So how does it affect TEC? The irregularities in the plasma density due to the solar eclipse of ionosphere causes the GPS signal to experience phase fluctuation, called ionospheric scintillation caused by solar radiation. And the effect of eclipse vary with the geographical location with various latitude, longitude, local time, and the geographical condition as the geometry of the eclipse formation with varying TEC. And the changes in TEC is one of the best methods to detect the ionospheric response to the eclipse. One of the events that directly affects the TEC is geomagnetic storm. So what is geomagnetic storm? Geomagnetic storm is a temporary disturbance of the Earth's magnetic field caused by the solar wind shock wave and the cloud of the magnetic field that interacts with Earth's magnetic field. These are the main objectives of our presentation, which are to obtain the TEC variation during the event of total solar eclipse on 22 July 2009 by taking it as a main event, July 17 to 21 as a pre-event, and July 23 to 27 as a post-event, and then compare them. And also to compare the TEC variation obtained from the IRX 2016 model and GPS TEC, and to study the effect of longitude and the low latitude on the ionospheric TEC during the total solar eclipse, and to study and check the validation of IRX 2016 model for the storm effect. Now we have come to the methodology. We have taken the TEC for total solar eclipse of 22 July 2009, which was the longest of the century, followed by the moderate geomagnetic storm, which lasted for 10 hours by using the two different methods. One is using ground-based GPS and other is IRI model. We can see in the map, the stations are highlighted and the eclipse was totally viewed from two stations, Ramite and the Biratnagar. And the eclipse was partially viewed from other stations, Sangari, Nepalganj, and the Saplecho. So how to retrieve TEC from the GPS measurement? Here we see in figure 3.2 in the flowchart, where at first GPS TEC data was taken by using the software provided by inapco.org, which gives the data in the next format. Then those data is calibrated in the understandable format, followed by plotting and data analysis by using the Python script. In table number 1, we can see the station information with latitude, longitude, with the duration of the solar eclipse time. The figure 3.2 shows the method to retrieve TEC from IRX 2016 model, where at first the latitude and longitude is given and the data was taken in our profile type with input and ASIC model as a history input. Then FO, F2, and FOE storm models are turned on to see the storm effect after the eclipse. And this is the only reason we are comparing the IRI TEC with GPS TEC, because there is no point to compare it for the eclipse effect as IRI is not effective for it. Then the TEC is measured. So this is the methodology to obtain TEC from GPS and IRI 2016 model. So let's move to the results. First of all, to see the eclipse effect, the TEC variation was only taken for the eclipse period but not for the whole day. In figure 4.1, we see the plot of totality regions only, in which there is a three vertical lines, in which the first line represents the start time of the eclipse, and the second line represents the maximum effect time, and the third line represents the end time of the eclipse. And we see a regular increase in TEC value in pre-event and the post-event, while there is a decline in TEC value in main event before 15 to 20 minutes of the maximum effect of the eclipse. In partial region, there is also decrease in TEC value during the main event, but the result is quite different than in the totality region, as the minimum TEC was obtained during the maximum effect of the eclipse. But in TPLG station, the minimum TEC was obtained before 19 minutes of the maximum effect of the eclipse, which is similar to the totality region. And the only factor common between them is the longitude, which changes between 84 to 86 degrees east. In this slide, we have done the comparison between GPS TEC and IRI TEC for the whole day. In figure 4.3, there is a notable variation in GPS TEC in all the events for all the stations. In overall study, we see an increase in the TEC value by 50% from pre-event to main event, while there is decrease in TEC value from main event to post-event. But in the IRX 2016 model, there was almost the same TEC variation in all the events for all the stations, and we do not see any particular effect of the storm. And we see the IRX 2016 model underestimates the GPS measurement. We see the other statistical information of GPS TEC in table number 2 and IRI TEC in the table number 3. The effect of solar eclipse on TEC vary with various latitude and longitude, which can be seen in figure 4.4 and 4.5. We see the latitude depends on the magnitude of the solar eclipse, but longitude does not. It is clearly seen in these plots that lower is the latitude, lower is the effect of the eclipse. But in figure 4.5, we see lower the value of longitude, higher is the effect of the solar eclipse. Because there is less value of TEC. Now we have come to the conclusion, and the whole research work can be concluded as the total solar eclipse is responsible for decreasing TEC value, the minimum TEC observed at the maximum path of the solar eclipse, and the time required by TEC to achieve the maximum reduction since the initial contact of the eclipse is less than the recovery time and is proportional to the magnitude of the eclipse, and geomagnetic storm is responsible for increasing TEC value, and the response of TEC to solar eclipse depends on both latitude and longitude. And the effect of solar eclipse is lower at low latitude region, while the longitude and the effect of the solar eclipse is inversely proportional to each other. And the ground-based GPS observations correctly reproduce TEC during the eclipse or storm period. And finally, the IR 2016 model underestimates the previous TEC and failed to simulate the storm effect. These are the references. Finally, come to the acknowledgement. I wish to show my gratitude to my supervisor, Dr. Enka Midoya Oru, for providing me a guidance, all the necessary information, and constant support. I would like to thank ANPA for providing the Python classes, which helped for all the plottings and organizing this conference. I would also like to thank my family and especially Mr. Ashok Suba for helping and supporting me throughout the work. The final slide shows the quick recap of whole presentation, and finally you can say IRS 2016 model failed to simulate the storm effect. Therefore, ground-based sequence TEC measurement might be worthwhile to be included in the IRS 2016 model to have better simulation on ionospheric solar eclipse and storm effect. Thank you.
Thank you, Agrima. Very nice talk. So, any question? No. So maybe I will have one question. So, Agrima, you said there was a geometry storm which has influenced the data. So, do you know how much? What was the DST index at that point? Like it was really intense storm or it was mild?
No, ma'am, I have not studied for the GST. I actually observed the effect of eclipse and the geomagnetic storms occur after the eclipse period. So I have also studied the effect of the geomagnetic storm on the TEC variation.
Okay, great. Thank you. So, any question one more time? Any question? No? Okay, thanks, Agrima. So,
Thank you, ma'am.
welcome. So, our next speaker is Elisa Podel from Prithvinarayan campus. And the title of the talk is Electronic Structure Circulation of Some Interstellar Molecules.
Hello everyone, Namaste. My name is Elisa Podel. I am Bachelor Fourth Year student of Prithvinarayan campus, Tribhuvan University, Pokhara, Nepal. Today I am going to give presentation of my research work, Electronic Structure Calculation of Some Interstellar Molecules. These are outlines of my presentation. Let me start from introduction. In modern astronomy, molecules are found everywhere in the universe, owing to rapid progress of spectroscopic observation, particularly in radio, infrared, and optical regimes. Chemical composition are widely used as a powerful tool for investigating physical condition and formation process of astronomical sources. So, astrochemistry is now one of the fundamentals of field for astronomy and astrophysics. Interstellar medium is the space between the star system that includes dust, gas, and cosmic rays. Space infrared observation have been providing information on understanding of interstellar trends. Dust grains in interstellar medium of galaxies affect their spectral appearance and their properties. Does life exist beyond Earth? Life as we know it is based on DNA, RNA, and proteins. The answer could lie in the interdisciplinary science of astrobiology. Before that, we need to identify molecule in interstellar space. Identification of molecules in the interstellar space may serve the references for the understanding of astrobiology. Some of the motivation behind this research work is listed as Yoshida et al. 2002 approached a vibrational analysis of large molecule by density functional theory (DFT) wave number linear scaling method. Molecules such as CH, CN, CH+, OH, NH3, H2O, H2CO, etc. has been identified by different authors. Springs et al. 1937, McKelly et al. 1940, Douglas et al. 1941, Weinberg et al. 1963 at different sources of interstellar medium. Currently, more than 200 molecules have been identified at different sources. Salika et al. Studied molecular structure and vibrational analysis of chlorobenzene using HF and DFT. J. Matthew et al. 2016 provided compelling evidence that the synthesis of complex organic molecule is driven by cosmic ray triggered non-equilibrium chemistry within interstellar ices at different as low as 10 Kelvin. ATSDR 1990 presented the toxicological profile for chlorobenzene. The objective of this research is to study electronic and spectroscopic properties of carbon chain molecules and their isomers, to analyze the electronic properties such as homolomo gap, binding energy, band gap, bond length, electron transfer, and orbital change, as well as we want to find answer of some questions like what is interstellar medium and what are significance of interstellar dust. And we can identify a molecule using its spectrum. We optimize the geometry calculated vibrational spectra by employing DFT B3LYP 6311G level of theory using Gaussian 09 program. Let us move to the resulting discussion part. First picture is optimized structure of SC3N molecule. It is 5-atom linear compound, so it gives 9 normal mode of vibration. All the fundamental mode of vibration have both IR and Raman activities. The calculated wave numbers were scaled by wave number linear procedure 1.0087 minus 0.0000163 by calculation. As spectroscopy is the study of the interaction between matter and the electromagnetic radiation, our major goal is to identify a functional group of molecule using its spectrum. That is, one calculated infrared spectra of SC3N and calculated Raman spectra of SC3N. Vibrational assignments of the functional group have been shown. A functional group vibrates in different modes as symmetrical, asymmetrical, scissoring, rocking, wagging, and twisting. I have taken 10 molecules in their properties: bond length, binding energy per atom, homolomo gap, dipole moment is calculated using Gaussian 09. Homolomo play vital role in predicting electrical and optical properties. Higher the gap energy indicates more stability of molecules and vice versa. This calculation is done for the interstellar molecules CO, C2O, HO, H2C2O, H2O, C3O, SC3N, and CS3NC, C6. calculated IR in Raman wave numbers using 6311G level of theory is given in the table. Calculated wave number were scaled by wave number linear procedure. The difference between these two spectroscopy is that IR depends on change in dipole moment and Raman depends on change in polarizability of molecules. And IR measures absolute frequencies which absorb radiation. Raman measures relative frequency at which sample scatters radiation. The conclusion of this research work is we studied the electronic and spectroscopic properties of carbon chain molecules and their isomers such as C2, C3, C2S, C2S, C3N, etc. The equilibrium geometry and vibrational wave function wave number has been calculated using DFT using Gaussian 09 program package employing 6311G. We analyze the electronic properties such as homolumo gap, binding energy, band gap, bond length, electron transfer, and orbital change of all the carbon chain molecules which are present in the interstellar medium. These are the references of this research work. Thank you so much for your attention. Thank you.
Thank you, Elisha, for such a nice informative talk. So it's now question, like it's time for question. Yeah,
Can you hear? Okay. So it's nice talk, Alyssa. So I have a question about you calculated using homolumo. So are you considering that as a solid matter or just a gas?
Elisha, are you muted?
She's unmuted.
She's unmuted.
Are you there? Oh, she's on the phone. Saji, are you there?
Excuse me. Yes, I can hear now.
Okay. Did you hear my question?
What?
I think you should repeat the question. Sorry. Yeah.
Yeah, no problem. So yeah, just as in in the homolumo model, did you model as a gas or is it like a solid? I mean, how does that homolumo came there? Because it usually comes in solid. So
I didn't understand question.
you have used somewhere like to get the spectrum like homolumo model for those organic compounds, isn't it?
Yes.
Yeah, that's my question is like, did you consider the material as a solid or a gas?
These are molecules.
Just in the molecular form, not in the solid form. Not like considering the other molecules interacts.
Sorry, this is my first project, so I have a lot to learn about this.
Okay, no worry, no worry.
Thank you for the question.
Okay. Thanks, Elisha. So we have we have time for one more question. Like
yes, please.
No, so if not, then thanks, Alicia. So now we can move to our invited talk, which is so Rishi, our portal is giving invited talk, and he's from NASA Goddard Space Flight Center and University of Maryland. And the topic of his talk is study of white light flares on M dwarf. Chandraji? Chandraji?
You are unmuted.
I-
And then let me make you presenter.
Cannot unmute me.
You are unmuted, right?
Yes, but I cannot share the content.
You must be able. Let me see again.
It's not active.
Okay.
Okay, I think I can do now.
Please.
Okay, can you
Yeah,
see my
we can
screen?
see that. Yep.
Okay, shall I start?
I think the chair wanna say something.
Okay.
yeah. Uh, so this is our invited talk by Rishi R. Powder, and he's affiliated to NASA Goddard Space Flight Center and University of Maryland. And the title of his talk is A Study of White Light Flares on M Dwarf. Here, go.
Thank you, Nishu. Namaste, everyone. I'm Rishi Paudel, and I'm a research associate at NASA Goddard Space Flight Center and University of Maryland. I'm very happy to be connected with Nepali physicists who are in different corners of the world. So today I am going to talk about flares on M dwarfs in general. I want to talk by giving a brief introduction about flares and M dwarfs. The flares are the explosive events which happen in the atmosphere of the stars so that the stars become very bright in different wavelengths. So this is the example of the star which is very quiet and it's not flaring. Of course, it is our sun, and this is the star which is flaring and it is bright in many wavelengths. To explain how a flare is produced, I would like to recall this basic physics concept. We know each magnet has North Pole and South Pole, and the magnetic field lines go from North Pole to South Pole. So there are regions in the stars which act as North Pole and South Pole, and the magnetic field lines go from North Pole to South Pole. The dark regions which we see on the surface of stars are the spots or the sun spots in the case of our sun. However, the magnetic field of the stars is not as simple as a bar magnet. There are multiple regions which act as south poles and which act as north poles. Now, I would like to recall you the example of a stretched catapult to explain how a flare is produced, which I believe that most of us have used it in our life at some point for fun. When we stretch the catapult, there is some energy stored in the rubber band of the catapult, which we call elastic energy. And when you release the stone or marble from the catapult, the energy of the rubber band is now converted to the kinetic energy of the marble or stone. So we can use this same concept to explain how a flare is produced. In this figure here, these are the magnetic field lines. The magnetic field lines get stretched because of the rotation of the star and because of the convective motion of the gas inside the star. As the star rotates more, the magnetic field lines get stretched more and more so that more and more energy is stored in them, which we call magnetic energy. A flare is produced when this magnetic energy is released by some mechanism, which we call magnetic reconnection. I want to play a short video to demonstrate how a flare is produced. Here, this is the photosphere of the star, which we can see in visible light. The thin layer just above the photosphere is the chromosphere, and the outer atmosphere is the corona. The photosphere has a temperature of few thousand Kelvin. The chromosphere is almost about 10,000 Kelvin, and the corona is uh, about few million Kelvin degrees. So this on the observation of our sun. Since the corona is very hot, it contains of highly ionized gas, ions, protons, electrons, and here these are the sorry, these are the magnetic field lines. One of them is coming out from the North Pole and one is going towards the South Pole. Now, when I play the video, you have to see what happens in this region to these magnetic field lines. Because of the motion of the gas, the ionized gas, the magnetic field lines come closer to each other, and finally there an event happens there. So this event is called magnetic reconnection. Um, as a result of this event, the magnetic energy is now released. So what happens after the release of magnetic energy? So the energy is now released in the form of soft X-rays in this region here, and it's also released in the form of energy of the particles which are trapped in this side, and they are ejected out as in the form of coronal mass ejection or highly energetic radiation, highly energetic particles, ions, electrons, protons. Likewise, the energy is also transformed to the kinetic energy of the particles which are trapped in this part of the loop. So the particles which are here in this side, they travel toward the photosphere after magnetic reconnection. Let me finish this video. Okay, in summary, during a flare, the magnetic energy is released in the form of thermal energy, mostly soft X-rays, the kinetic energy of ions and electrons, the kinetic energy of coronal mass ejections. As a consequence of this, the flare energy is emitted in various wavelengths. In general, X-ray to radio wavelength. Each wavelength probes different aspects of flaring events in different atmospheric height of the star. Now I want to give you a brief introduction about M dwarfs. We classify the stars in various spectral types depending on their effective temperature, masses, and radii, and each spectral type is assigned a letter like O, B, A, F, G, K, M. In this sequence here, the O stars are the hottest star and they are the massive star. They are the most massive star with effective temperature of 40,000 Kelvin. So the effective temperature is simply the temperature of the photosphere. Likewise, the M stars are the smallest stars and they are the coolest stars. Since they are the smallest stars, they are also called M dwarfs. They have effective temperatures in the range 4000 Kelvin to 2400 Kelvin roughly. Since they emit most of their light in red wavelength, they are also known as red dwarf. Our sun has a spectral type of G and effective temperature of about 6000 Kelvin. The M dwarfs are the most populous objects in the sky. Almost 70% of the objects in the Milky Way galaxy are M dwarfs. So if we are able to throw a stone that can go outside of the Earth and land in one of the stars in the Milky Way, so 70% of the time the stone will land in an M dwarf if it lands on a star. The M dwarfs have masses less than 0.6 solar masses and they have radii less than 0.6 solar radii. We further divide the M dwarfs into various sub-spectral types M0, M1, M2, likewise M8, M9. M0, M1, M2 are the early M dwarfs. M4, M5, M6 are the mid M dwarfs. M7, M8, and M9 are the late M dwarfs. So the early M dwarfs are hotter than mid M dwarfs, and the mid M dwarfs are hotter than late M dwarfs. So late M dwarfs are the coolest M dwarfs. After launch of Kepler and TESS mission, we now know M dwarf host planet. In average, every M dwarf has two planets with orbital period less than 200 days. So this result is based on Kepler data. These are examples of some famous M dwarfs which host planets. So this is TRAPPIST-1 system, which has 7 planets, and this is TOI 700 system, which is also M dwarf planetary system, and it has 3 planets. So this system was recently discovered by our team at NASA Goddard. So what about habitable zones of M dwarfs? The habitable zones here, they are shown by the blue region around the stars. So they are the regions in which the water can exist in liquid state. So if the planet is outside of the habitable zone, like was here, the temperature is very low and the water freezes. And if the temperature is towards the star outside of the habitable zone, then the temperature is very high and the water evaporates. So the planet should be in correct location for the water to be in liquid state. Since the M dwarfs are cool stars, they are less luminous, they have habitable zones very close to them than in case of our sun and the hotter stars, so that the planet orbiting the M dwarfs in the habitable zone get the correct amount of radiation. We know that the radiation scales as the inverse of square of distance. In general, the average habitable zone distance for M dwarf is 0.15 AU. Here I show a more closer comparison of our solar system and M dwarf planetary system. We can see the habitable zone of M dwarf lies inside the orbit of Mercury. We know that the nearest planet Mercury is at a distance of 0.4 AU from the Sun, and we also know we are at a distance of 1 AU from our Sun. So we can see the habitable zone of the M dwarf is very, very close to them. There are some problems when the habitable zones are very close to the stars. The M dwarfs have very strong magnetic fields, so they can produce very strong magnetic fields, which are they can produce very strong flares which have energies more than 10,000 times the biggest flare which we observed on our sun. The energy of the biggest flare observed on our sun so far is 10 power 32 watts. Because of this, when a very big flare happens on the M dwarfs, it's very easy for the high energetic radiation and the highly energetic particles to reach the planet that is orbiting the M dwarf, which is in its habitable zone. So those radiation and the particles can easily destroy the atmosphere of the planet, or they can disturb the thermoequilibrium of the atmosphere of the planet, or they destroy the ozone layer of the planet. If you are following the news, you might have seen this poster in which a planet is orbiting a star AU mix. So the star is here in the middle. So this is a very young star um, with age of like 20 million, I think. Uh, I have to check that. Sorry for that. So it's very young star, and it is a flaring star. So it's producing very large flares. And there is a planet which is going just uh, which is orbiting this star. So this system was discovered recently, and the publication was made in Nature Journal last month. And we are analyzing the flares on this system. By the way, we are observing this star today by using various telescopes. We are using TESS, SWIFT, and NICER to observe the planet transit today. The main point is that we need to study the flares on M dwarfs to study if the conditions on planet orbiting them are suitable for habitability or not, and find an answer to this very, very big question: are we alone or not? Do we have friends like them somewhere out in the outer world? Maybe yes, maybe not. So we use various facilities for studying the flares. We use test data and Kepler data to study the white light flares, which are also called the optical flares. Uh, The test provides continuous high precision long baseline data for a minimum of 25 days for each star, and the Kepler provided high precision data for each star for more than 70 days. By the way, Kepler mission has ended. It ended in 2018. We also use some ground-based observatories to study flares on M dwarf. How do we study flares? We analyze the light curves which are obtained by TESS mission, Kepler mission, and the ground-based observatories. A light curve is simply the plot which shows the variation of flux with time. So in this plot here, the flux is in y-axis and time is in x-axis. This is the light of a boring star in which we did not see any flares. The variations are due to the noise in the data. But this is the light curve of a flaring star in which we can see many spikes in the light curve, and most of those spikes are the white light flares or the optical flares. By the way, uh, the flares which we study by using TESS and Kepler are optical flares. I think I mentioned it earlier also. The flux here, this corresponds to the photospheric flux, that is when the star is not flaring and when it is in its quiescent mode. These are the examples of white light flares. The flare can have a single peak or multiple peaks. If it has a single peak, then it is called classical flare, and if it has multiple peaks, it is called a complex flare. Now I want to show you some of the results of my project. This is the sample of M dwarfs which I studied by using Kepler K2 short cadence data. That is, the data was taken for every 1 minute for about 70 days up to 90 days for each star. So far, I studied the light curves of 28 M dwarfs and identified the flares on 18 M dwarfs. Here is one of the results from my project. In this plot, I compared the flare rates of different M dwarfs, M5, M6, M7, M8, and M9 M dwarf. In general, what I found is that the mid M dwarfs have a higher average flare rate than the late M dwarf. The M5 dwarf have an average flare rate of 1 flare per day, and M6 M dwarf have an average flare rate of 1 flare per 2 days. The late M dwarfs have lower flare rates. However, the flare rates also depend on other factors like age, multiplicity. I have not taken into account these factors, so the results may slightly change if I take into account these factors. If we observe the star for a long time, and if we can observe many flares, we can make a plot between the log of energy of the flares and log of the cumulative frequency of the flares. And we can feed the data by using a straight line. This type of distribution is called power law distribution. And this type of plot is called flare frequency distribution. Here I am showing you the flare frequency distribution of one of the stars in my sample, TRAPPIST-1, which has 7 planets. So we can use this type of plot to estimate or to predict the number of flares that can happen on a given star with certain energy. By the way, the parameters here are the fitted parameters for this line. The slope is negative 0.6 and the intercept is negative 1.65. And this corresponds to energy 10 power 30 ergs. So for this star, we predict that a flare with energy 10 power 31.5 or greater than that occurs at a rate of 1 flare every 16.4 days, and a flare of energy 10 power 30 hours or more than that occurs at a rate of 1 flare every. So this type of plots are very important to estimate the flares with certain energies that can happen on a given flaring star. We know that the late M dwarfs have effective temperatures less than approximately 3000 Kelvin. We wanted to know if the late M dwarfs can produce very big flares, the flares with energies greater than 10 power 33 hours. After the analysis of the flares on some late M dwarfs, we can say that they can produce very strong flares. So these are the examples of very strong flares which we observed on the late M dwarfs M7, M8, M9. All of these flares have energies more than 10 power 33 hours. So this flare was observed on a very young 1 to 2 million year M7 dwarf, and this flare was observed on a very young 700 million year M8 dwarf, and this was observed on M9 dwarf. We can see the amplitude of the flares, which is the peak, the height of the peak flux from the quiescent zone is about 50 times in case of all the three flares. Now I want to give you an update of the current project. I'm using different facilities to study the flares in various wavelengths. So it's very important to study the flares in different wavelengths because I mentioned that flare energies are emitted in various wavelengths. So it's important to understand the correlation between flare energies in different wavelengths to estimate the total energy budget emitted during flares. Such estimate will provide valuable inputs into exoplanet atmosphere and climate model. So I'm using TACE, Swift, and NICER, and some ground-based observatories to study the flares on different stars in different wavelengths. These are the examples of some famous stars which I'm studying now, and some of them have planets like the star like Proxima Centauri, MiG, and YGCMI have some planets. Now I want to show you some of our results starting from test data. These are the light curves of two flaring stars, EVLAC and Proxima Centauri. We can see spikes in the light curves, which are the white light flares. And in average, we observed more than one flare in each star. Here I show you some of the UV flares which we observed on one of the flaring star, EVLAC. The cadence size is about 10 seconds. Almost all the flares have very strong duration ranging from less than a minute to few minutes. One notable property of the UV flares is that they have relatively higher amplitudes. We can see that even the weakest flare has amplitude of 2 times the quiescent level, and the strongest flare has amplitude of more than 50 times the quiescent level. If we see the light curve of EV lag here in optical wavelength, the largest flare has an amplitude of 1.3 times the quiescent level. So I don't have more time to go over the remaining slides. I can go to the summary now. We are in process of analyzing more flares on other stars, which were observed simultaneously by TACE, Swift, and NICER. And here's the summary. The mid-M dwarfs have a higher average flare rates than that of late M dwarf. The late M dwarfs are also capable of producing super flares. The white light flares and UV flares are more frequent than X-ray flares. The UV flares have short duration and are less energetic but have higher amplitude compared to the white light flares, and the large UV flares are very rare. Thank you. I'm ready to take any questions you have.
Thank you, Rishiji. Very nice. So
Thank
in our
you.
next section, we have a whole bunch of questions. So, Suman Satyalji, do you want to say your question, or should I read it from here? Sumanji?
You can read it, or yeah, Rishi can read it.
Yeah. So the first question is, why is the sun's
Okay.
corona hottest compared to other internal regions?
It's a big mystery. Actually, we don't know the exact answer, but one of the reason it might be because the heat is produced because of very small flares, which we call nanoflares. But this theory is not proved yet. It's a very big mystery.
Yeah, and then there is another wave turbulence theory. Like there are a whole bunch, but still it's a mystery. Yeah. So the second question is, why are M dwarf in so much abundances? Are they the oldest of the stars?
I don't think they are the oldest, but since I'm not into that part of my research, so to be honest, I don't know the exact answer for that. there may be something with to do with the scaling in the formation process, but I don't have the exact answer now.
Okay, so the now last question is again from Suman Satyalji. So due to the high radiation, I think this is his more comments. Due to the high radiation from M dwarfs that can extend few AU away, my personal conclusion is there is no real habitual zone for M dwarfs. Any comments?
It depends because it's not that the M dwarf are active all the time. The activity also depends on the age of M dwarf. So if the M dwarfs are relatively old, then they may be less active, and the conditions may be favorable at some point. But we are still trying to analyze the flares. We are actually trying to see how the activity of the M dwarfs evolve over time. Then we can say. Um, I think it's not 100% that the
Uh,
flares can affect the planets all the time. There may be some point the flaring activity can stop and the condition can be favorable at some point.
I think that it's more dependent on the ultraviolet radiation. So basically, even if
Mhm.
your flare is very intense, but if your ultraviolet intensity is very low, then it's highly likely to have a biogenesis in those exoplanets.
Yes. In the beginning, we need UV light. That's correct.
Yeah, so I'm all talking about the intensity of the UV light because you need the
Uh-huh.
UV light for the biogenesis. And if you
Yeah.
have a very intense UV light, then it's going to destroy, all those biogenesis factor. So
Uh,
even your flare is very, strong or intense, it totally
uh-huh.
depends on like, what is the intensity of the UV radiation it
Uh,
producing during the flare.
Yes, I agree. But yeah, we need to study how the activity of the M-dwarfs evolve over time and how if they have corona and how does that evolve over time. So we just expect that there may be some point, maybe after some giga years, the M-dwarf may be less active and the planet can have right conditions.
Right. And I have last question for you. So what effective temperature, like how many temperature you use to, feed the underlying continuum of your, SED?
For the players,
Yes.
basically, we use a black body temperature of 10,000 Kelvin for the white light flares, but for the X-ray flares, we feed the SED maybe some million degrees Kelvins,
So million degree Kelvins.
and that's for X-ray flares. But for the UV flares and the white light flares, it's only about 10,000 or maybe it may go up to 15,000 Kelvin.
Yeah. Okay. Yeah.
Great.
So basically, like the AGV stars, they at least need two or more than two black body temperature to feed the underlying continuum. And it seems like
Yeah,
you only use one effective temperature. So I was wondering how reliable is that?
Yeah, that's so there are many there's some study. So the range mainly goes from 9,000 Kelvin to 16,000 Kelvin. That's what we have obtained from many research works. So that's what we believe for now based on the data we have for the optical flares and the UV flares. And but as we know from the corona of the sun, we may need to fill the spectrum by using some a million Kelvin degrees for the X-ray flares.
Thank you.
Okay, now let's move to other question. That's from Basudev Ginure. How magnetic storms from M dwarf penetrate ionosphere and can affect ozone layer?
Can you please repeat the question?
How magnetic storms from M dwarf penetrate ionosphere and can affect ozone layer?
Uh, I don't have the exact answer, but it's a two-step process. The high energetic particles or the ions that enter the atmosphere, they cause the photodissociation of I forgot the exact molecule. So it is a two-step process. It does not directly destroy the ozone layer, but there is some two-step process to destroy the ozone layer.
Thank you. So there will be one more last question, like we can take. So this is from Kafle. In magnetic reconnection, it looks like the magnetic field lines have tendency to cross each other. Could you please comment on that? Thank you.
Can you please repeat the question?
In magnetic reconnection, it looks like that the magnetic field lines have tendency to cross each other. Could you please
Yes.
comment on that?
They don't cross each other. There is no any violation of. I want to go back to my slide. Basically, there is no violation of any things like the magnetic field lines don't cross each other. Actually, they are oppositely directed magnetic field lines, so they just connect and follow the principles of electromagnetism. There is no any violation of such things.
Great. Thank you, Rishiji. It was
Thank
really
you.
nice informative talk.
May I ask a question real quick? Excuse me.
We are out. We are almost.
Just a basic question.
Sure.
Hello, sir.
Yes.
Sir, I was first of all, thank you for the talk, and I'm a very physics student. I'm here with a very basic question, sir. So I really wanted to know the basic difference between the solar flare and coronal mass ejection. I mean, I'm really new to this topic, so I was really interested in these two terms.
So they are not actually very different things. They are related to each other. We don't know which is the chicken and which is the egg. So it may be the flares are caused because of the coronal mass ejection, or it may be the coronal mass ejection are the result of flares. But there is some relation between the flares and coronal mass ejection. So we don't have the exact answer for now.
And last one, sir. Do you have time?
No, I think we are out of time. Sorry.
Thank you very much. Thank you, sir.
Thank you.
Thank you. So our next talk is from Silva campus, and the title of the talk is GPS observation of ionospheric TEC variation during the 26th December 2019 solar eclipse. Chandraji? Oh, okay, good.
Good morning, everyone. Respected chairperson, ANPA family, Nepal Physical Society, and all respected professors. It is a great honor to be here presenting my research work entitled GPS Observations of Ionospheric TEC Variation during the 26 December 2019 solar eclipse. This work is carried out under the supervision and guidance of Professor Dr. Narayan Prasad Chapakai, and at all stages, my colleague Susan Prasad Gautam has helped me equally. This is the overview of my work. As we know that the layer of the air above the Earth's surface is called atmosphere. It extends up to a height of 1600 km from the Earth's surface, and the Earth's atmosphere is further divided into 5 different layers. Among them, the ionosphere is the dynamic layer of the upper atmosphere that extends roughly from 60 km to 1000 km, and it is a region that includes the thermosphere and parts of mesosphere as well as exosphere. If we look at the electron concentration in the ionosphere, it only amounts to 1% of the neutral concentration. However, the presence of this electron has a profound effect on the behavior and properties of the ionosphere. The vertical structure of the ionosphere, as we can see from the diagram, is further divided into D, E, and F layers, and these layers are responsible for the reflection and propagation of the radio waves in the Earth's surface. One of the most important parameters for providing the crucial information on the ionospheric activity is total electron content. The term itself suggests its meaning, that is, TEC is an integral of electron density along the path between the GPS satellite and the ground receiver. The ionosphere can cause delay to the GPS signals, which is proportional to the TEC along the path of satellite and the receiver, which is placed at ground. And this quantity is strongly affected by solar activity and solar distribution as well. Different natural and artificial phenomenon affects the physical and chemical behavior of the ionosphere, and this quantity, that is DEC, helps to address them. Here is a cartoon which describes the ionospheric delay caused by the presence of free electrons and ions present on the ionosphere to the GPS signal. So here is one GPS satellite, and this is the ground receiver. The presence of free electrons on the ionosphere added a transmission delay for the GPS signals, which we called ionospheric delay. As we are concerned about the GPS observation of ionospheric TC variations, let me describe what actually is GPS. It is a constellation of 24 satellites placed into orbit at an altitude of 20,200 km. They work in any weather condition anywhere in the world 24 hours a day to provide time and location. These GPS satellites send signals to the receiver on L1 and L2 carrier frequencies. And these frequencies are exposed to various factors in the ionosphere, which can change the direction and velocity of the GPS signals, and this might lead to positioning error as well. So the ionospheric condition must be monitored effectively. If we have a look into a cartoon published by NASA, we can see that the GPS signals are continuously transmitted under undisturbed ionosphere, whereas during disturbed period, ionospheric scintillation occurs, and this might lead to positioning error. A solar eclipse occurs when the moon passes between Earth and the sun, and it thereby totally or partly blocks the sun for a viewer on the Earth. Talking about the annular solar eclipse, the sun appears as a very bright ring surrounding the dark disk of the moon. Actually, the investigation of the ionospheric variability during the rare events like solar eclipse provides a great opportunity in order to study the effects of this phenomenon on different parameters of the ionosphere. And also, ionospheric responses to the solar eclipse over a short period of time can be studied. Actually, what happens during a solar eclipse is the amount of solar radiation reaching the Earth diminishes. As a result, the production of the plasma is reduced. So we expect a lower electron density in the ionosphere during solar eclipse, as we can witness it from previous studies as well. For this work, a large number of literature was reviewed, and almost all shows decrease in electron density during the solar eclipse. In 1998, Abramovich suggested that the depression in TC is actually independent of latitude and longitude. However, after 2008 and 2009, a large number of study advocates for the latitudinal effect of the eclipse. With this curiosity, we were also concerned about the ionospheric responses in terms of TEC during the eclipse, along with the effect of latitude and longitude. Regarding the data and methodology, on 26 December 2019, an annular solar eclipse having a magnitude of 0.96 occurred, and it actually lasted for 3 minutes and 40 seconds at the point of maximum eclipse. A globe view can be seen from figure 8 as well. In context of Nepal, only partial eclipse was visible. We then used GPS to observe the TEC data over the 5 different stations of Nepal, which can be seen from figure 9, and the more detailed information about this station can be obtained from the table. Actually, these data are provided freely by UNESCO in Drynex format, and then we later convert it into user-readable format for further analysis. We collected the data by dividing the study into 3 different scenarios. 5 days before the event, which we consider as pre-event, during the day of the eclipse, that is main event, and 5 days after the eclipse, that we consider as post-event. Based on the methodology discussed above, the temporary variation of TEC before, during, and after the partial solar eclipse was studied using the GPS measurements, as we have mentioned before. The time series of TEC provides a good basis to study the temporal effect of the solar eclipse on the TEC diurnal pattern. It can be seen that the mean values of BTEC during eclipse hours are low as compared to other days. It is worth noting that there is significant depletion in the level of TEC as an effect of the partial solar eclipse. We also observed that The minimum level of TEC persists around 2 UT to 14 UT, and then it slowly recovers after the sunset. In addition, the depletion of the TEC is different for each station, which is actually related to their geographical location. We also compared the TEC level during the solar eclipse of 26 December 2019 with the mean TEC of most 5 quietest days of the month provided by WDC Kyoto, and this result also revealed that there is significant reduction in TEC during the eclipse hour. This can be seen from the diagram, where we can clearly see the reduction as compared to the quiet days. And this result shows the depression of TEC in terms of percentage during the day of the eclipse than the pre-event days, and along with the increase of TEC after the day of the eclipse that we call a recovery phase in the post-event days. Here we clearly observe that the VTEC difference between the day of the solar eclipse and the days before the eclipse event roughly exceeds by 15%. Roughly, it exceeds by 15% in all stations, whereas in some cases it is greater than 20% as well. However, the rise in TEC level after the eclipse event exceeds roughly 10%, and in some cases it is greater than 30%, as witnessed from the figure. At last, we calculated the difference of average VTEC during the hours 2 UT to 6 UT, focusing on the eclipse hour, on the eclipse day and normal days, and then we expressed it in percentage. As we were concerned about the latitudinal effect on the vertical to electron content during eclipse hour, what you observe that the depression of TEC for the station Johnson, which is at high latitude among the mentioned station, reached nearly 23% compared to a quiet day. Whereas the station Biratnagar was found to have a minimum percentage of BTEC difference during the eclipse hour. This supports the fact mentioned by Kronkowski that the depression was more effectively developed towards the high latitude and then it moved towards the east. Finally, we came into the conclusion that the TEC values at all those mentioned stations showed reduction by 1 to 4 TECU that actually corresponds to 10 to 30% TEC depletion during the eclipse hours, which are actually consistent with earlier reported studies as well. In addition, comparable reduction in TEC were seen for few more hours even after the early morning eclipse. This is where the importance of our study holds for future reference. Further, we also noticed that the depression was more effectively developed towards the high latitude and then it actually moved towards the east, which agrees the previous studies as well. This all ensured that the response of TEC to the solar eclipse depends on the latitude as well as the longitude. And these are the few references that we had gone through in details to benefit our research work. Finally, I would like to express my sincere, heartfelt acknowledgement to Professor Dr. Nayan Prasad Chapagai, all the teachers of Department of Physics Partner Multiple Campus for their valuable suggestion and guidance. And I would also like to thank ANPA family for providing the platform to present this work.
Thank you, Ashok Silva. Really nice talk. So, any comment, any question?
I think there is one question in the comment section.
Yeah, this is from Suman Satyal to everyone. Does TEC levels affect health? Is there such research?
Actually, TEC level does not affect the health, but it concern about the positioning of the satellites. and the reflection of the radio signals that gets reflected to our surface. So concerning about the previous studies, there is not a single study that concern about the uh, that the TEC affects health factor.
Thank you. So I have one comment. So you are looking at annular solar eclipse, and there were Agrima like looking at total solar eclipse. So have you like compared the data set, like which has more like change in the TEC?
Yes, ma'am, we do that. We are preparing another paper which deals with two solar eclipse, and what we found that this depends upon the path of totality, the path and the obstruction rate as well.
Okay,
So we are dealing on that and preparing on the paper.
great. Thank you. Thanks.
Thank you, ma'am.
Thank you.
I have
I
one
have
question.
Our, uh, our next talk is from Baburam Sharma. He's from Prithvi Narayan campus, and the title of the talk is The Location of Metric Type 2 Radio Burst and Associated Coronal Mass Ejection.
Good morning, everybody. I'm Baburam Sharma from Prithvi 9 campus, Pokhara. Currently, I'm doing MTech in Space and Atmospheric Science from PRL Ahmedabad in collaboration with Andhra University according to the SESTAP Andhra University agreement. It is a UN outer space program. Today, I am going to present a part of my research that have been carried out under the supervision of Dr. Bhuvan Joshi, Associate Professor, Udaipur Solar Observatory Physical Research Laboratory, and Professor Narayan Prasad Sabagai, Tribhuvan University, Amrit Campus, Nepal. I'm not going to detail about the solar structure. My current research topics related to the solar activities, mainly solar flares and CMEs in the solar atmosphere. Therefore, I start my presentation directly from the solar flare. Solar flare is the sudden brightness enhancement on the solar atmosphere. During the solar flare, huge amount of energy of the order of 10 to the power 20 to 10 to the power 25 joules is released within a few minutes. Solar flares are generally observed in different wavelengths, that is 94, 131, 171, 193, 304, 335, and 1600 angstroms. These multi-wavelength observations of solar flares demonstrate complex temporal and spectral variability in the energy release forces at different height levels. According to the X-ray flare intensity, solar flares are classified into different classes A, B, C, M, and X. The range of intensities are summarized in the table given in the slides. The right lower corner figure in the slide shows the gauge light curves corresponding to 1 to 8 angstrom red color and 0.5 to 4 angstrom in green color. Radio burst. Solar radio emission of a solar flare is called radio burst. When non-thermal electrons are accelerated during the solar eruption process, solar radio burst occurs. There are different types of solar radio burst: type 1, type 2, type 3, type 4, and type 5. The observational features of these solar radio bursts are summarized in the schematic diagram shown in the slide. My current research has two prime objectives. First one is statistical study of the type 2 radio burst observed by UTE Callisto during the period from 01 January 2011 to 31st December 2014. My second objective is to estimate the different parameters using dynamic radio spectrum such as plasma frequency, electron density in corona, heliocentric distance of burst, shock speeds, and CME height. Observation and data analysis. Our study is based on the E-Callisto data observed by UTE stations during period from 1st January 2011 to the 31st December 2014, correspond to the rising, maximum, and decay phase of the solar cycle 24. Our study started from the identification of different radio bursts. We first examined quick look data available at E-Callisto website and found several radio bursts of different types during this period. From this, we separate out the type 2 radio burst. We found 38 type 2 events during our study period observed by the UTE Callisto station. These representative events are compared with the GOES flares list and SOHO last 4 CME catalogs for flare and CME information. Estimation of type 2 parameters such as shock height, drift rate, and shock speed. To illustrate the estimation of type 2 parameters, I have considered the one event which occurred at 5th November 2014. I have developed this spectrogram shown in the slide by using the ideal programming from the fit file from eCallisto stations. To calculate the different parameters, I need one starting frequencies and another is ending frequencies and their corresponding time events. To estimate the parameters, I have used well-known equations which relate the frequency and the plasma density. Then I use the nucleic density models. Here I use the 4-fold nucleic models. From this, I estimate the radial distance of the solar burst at starting frequency and at ending frequencies, and the corresponding height for these frequencies is estimated. From these distances, by using the relation v equal to dr by dt, I estimate the speed. My estimated shock speed for this event is 874.98 km per second, and the estimated drift rate is 0.23 megahertz per second. I repeated this estimation process for all 38 events, and they are listed in the present slide. And finally, I developed the catalogs. In this catalog, from column 2 to column 8, there are the information about the solar radio burst. From column 9 to 14, there are the informations about the associated solar flares. And from column 15 to 22, there are the information about the associated coronal mass ejections. Now I come to the statistical analysis of the radio burst. From the bar diagram, we came to the following conclusions. Young class flare has the dominant role, about 54.4%. More type 2 events are occurred during 2011 and 2013 though the solar maxima is obtained at January 2014. Type 2 shock speed mainly varied from 400 to 1200, about 68%. And most of the type 2 radio burst has the starting frequency between 51 to 100 megahertz, about 65%. There is a good correlation between type 2 radio shock height with the starting frequency, good correlation between drift rate and the starting frequency and ending frequency. The drift rate increases with increase in starting frequency as well as ending frequencies. A very poor correlation is seen with the type 2 shock speed, CME speed with the flare impotence. Now I come to the estimation of type 2 shock height and CME height. For the estimation of type 2 shock height and CME height, we have used the flare onset methods where the CME is assumed to be launched at the flare onset time. At the flare onset time, CME is assumed to be launched at least from the height of the 1.25 solar radius. This limitation for the CME launch was chosen because it corresponds to the boundary of the cavity of the above prominence. For the estimation of initial accelerations, I have used a very simple kinematic equation V equal to U plus A delta T, where delta T is the time difference between the flare peak time and flare start time. By using this acceleration, I have estimated the distance traveled by the CME during the time interval solar radio burst start time and solar flare start time. By adding this distance with the boundary cavity limit of 1.25, we got the projected height of the CME. I have repeated this process for all 35 events. The initial acceleration of CME shock height, and CME height are listed in the table as shown in the slide. To the final conclusions, type 2 shock height varied from 1.19 solar radius to 1.99 solar radius, and the drift rate varied from 0.8 megahertz per second to 0.64 megahertz per second. The estimated CME height at the time of type 2 initiation lies between 1.25 solar radius to 1.75 solar radius. The difference between the type 2 and CME height is estimated. We found that about 74.3% events, this difference delta R is positive, which indicates that the type 2 radio bursts are located at or above the leading edge of the associated CME. The maximum distance by which the CME leading edge ahead of the type 2 radio burst position was 0.41 solar radius. These numbers are consistent with the stand-up distances, which is less or equal to 1 solar radius from the leading edge of the CME, where the shock is expected. In our present study, 8 out of 25 events, type 2 radio bursts are behind the leading edge of the corresponding CME by 0.3 solar radius. This separation is less than the thickness of the order of 1 solar radius for the frontal structure of the CME. In summary, our result indicate that the metric type reported in this study are likely due to the image shock driven by the CMEs and formed in front of the leading edge of the CME. These answers, lastly, acknowledgement. We are grateful to eCallisto Network, UT eCallisto Stations, NASA, Stereo, LASPO, SDO, AIA, NOAA, SWPC make their data available online. I am thankful to SESTAP affiliated to United Nations for providing me the financial support for this work. Special thanks goes to PRL, which provide me peaceful platform and easy access for the resources for this research, and very special thanks to Association of Nepali Physicists in America, ANPA, for giving me this platform for presentation. Thank you for your kind attention.
Thank you for the wonderful talk. So now we can take question. So questions. So we have okay. So we have a question from Rishi Porelji. So is there any correlation between the type 2 radio burst and the coronal mass ejection of Sun?
Hello.
So there is one question. Is there any correlation between the type 2 radio burst and the coronal mass ejection?
Yeah, ma'am. There is a very good correlation, about 78% correlation I found. And in my present study, I found that out of 38, 25 events are associated with the flares as well as the CME.
Okay.
So is there any hint that the CME are suppressed during some radio burst?
Yes, Rishiji, please. Please repeat the question.
So I want to know that if some of the CMEs are suppressed by the strong magnetic field present in some of the strong magnetic field region of the Sun, do we have any hint of that?
Sorry, regarding that suppressions and others, okay, I am not going on that part. Okay.
It's fine. Okay, yeah.
Hello. Hello. Okay. So
Very good.
let's move to the next talk. First, thanks, Basu. So Baburam Sarmaji. Yeah, thanks, Baburam Sarmaji. Now, let's move to the next talk by Basudev from Tribhuvan University, and the title of his talk is Ionospheric Perturbation Due to Mexico Earthquake as Measured from GPS Tech Data. So here we start.
morning and good evening, everyone present here. I am Vasudev Gimiri, going to present atmospheric perturbations due to Mexico and Nepal earthquake as measured from GPS-TC data. I am belongs to Institute of Science and Technology, Center Department of Physics, Tribhuvan University as a PhD student. On the surface of the sun, there is a convection of rotation. This convection of rotation produces the dynamo of magnetic field. Due to this dynamo of magnetic field, masses of ejection from the surface of the sun. This is called the coronal mass ejection and solar wind. This solar wind and coronal mass ejection is responsible to produce the substratum and superstratum on the in the magnetosphere. This magnetosphere directly influence the ionospheric disturbances, or it produces the it produces the waves on the ionosphere, which fluctuate the total electron content of ionosphere. Not only this, there is another way of disturbance the ionosphere, means terrestrial events. Due to the terrestrial events, tropospheric disturbances occur, and which produce the wave in the middle atmosphere. This wave is responsible to disturb the ionosphere. My aim is to find out is there any abnormal signature because of the earthquake in the tropospheric as well as the ionospheric disturbances. So we choose the earthquake anomalies behavior of the ionosphere. For this, we have to take the total electron content of ionosphere. This total electron content is the total number of electrons in the cylindrical tube of cross-section area 1 meter square taken from the base of the ionospheric cell to the top in the lines joining the GPS receiver on Earth to the satellite. Here, n is the electron number density, 1 T is unit equals 10 to the power 16. This is the formula to find out the slant total electron content, which is the function of the two L-band frequencies and pseudo range of L-band frequencies. To find out the abnormal behaviors, we must have to calculate the vertical total electron content. This vertical total electron content is the function of latitude, longitude, and local time. So this slant total electron content is converted into vertical total electron content by using the mapping function as shown in the geometry. The TEC data will obtain from the International Global Navigation Satellite System in the site, and we convert to this data obtained from the UNEPO into vertical total electron content by using the GoPCMA software. To find the abnormal behaviors of the vertical total electron content, we had to BTS's anomalies can be performed by using 15 days moving median XBAR and associated interquartile range IQR. Construct the upper bound XBAR plus IQR and lower bound XBAR minus IQR. For the confidence level, the expected value of XBAR and IQR are mu and 1.34 sigma respectively, where mu is moment and sigma is standard deviation. If an observed BTC falls out of either the associated lower or upper bound, we declare with the confidence level of about 80 to 85% that the lower or upper abnormal signals is detected. To find out the abnormal behaviors of the Mexico earthquake, we choose the one of the stations which is very nearby the epicenter. To find out the GPS data to find out that this is the GPS station which is very nearby the epicenter, and then we calculate the vertical total electron content. Then after lower bound, upper bound, median, and find out the little bit find out the very abnormal behaviors shown in 2 or 3 days before the earthquake, which is indicating by the blue vertical line of magnitude 8.1, which is held on 8th of September 2017. So here indicated upper bound is because of these, it may be because of the precursor signature of the earthquake. We also find out, is there any abnormal because of the solar indices or magnetic storm? but we could not find out any types of the solar indices and magnetic storms before that earthquake. So it is indicated that 2nd, 5th, and 6th September's the which in the 2nd, 5th, and 6th September, the vertical total electron content value exceed the upper bound and delta VTC. It may be because of the earthquake happening in the 8th September. We also choose the Nepal earthquake. To find out the abnormal behavior of the Nepal earthquake, we choose 4 stations. Three stations are very near by the epicenter, and one of the stations is very far, little bit far from the epicenter. To find out the similar ways as above mentioned, we calculate the lower bound, upper bound, median, and also choose the DXT, F10 point solar flux, and KP indexes to find out if there any abnormal behavior because of the solar indices or magnetic storm. But we could not detect any types of the anomaly because of the solar indices or magnetic storm. And then find out the 2 abnormal behavior is find out in the Silime stations before the one day before the earthquake, which is indicating by the 0 is the day of earthquake. In the 0 is the day of earthquake, and one day before the earthquake, we found the median value, BTC value is crossing the upper bound, and 9th day before the earthquake also the VTC value crossed the upper bound. It may be because of the earthquake happening in the magnitude of 7.8 in the day of in the 24th of April, and then so similar result is found. Similar result is found in GSRE stations, which is 27 kilometers from the epicenter. We also found exactly similar day, one day before the earthquake, and then 9th day before the earthquake. We found the similar peak abnormal earthquake anomaly signature is found, and then similarly. We also used one of the stations, KKN4, which is 90 kilometers from the epicenter, and found the similar one day and 9 day before the earthquake in here. Now, one of the another station, which is a little bit far from the epicenter, is found only one precursor signature is found. Means only one pre-earthquake anomaly is found one day before the earthquake. We could not detect the 9th day before the earthquake. It may be it may be the ionospheric perturbations also depends upon the distance from the epicenter. So we conclude that pre-earthquake ionospheric anomalies observed in Mexico and Nepal earthquake from GPS-TEC measurement process. Similar result was obtained for different earthquakes at different places, like is Hayakawa or Little, etc. The value of GPS-TEC remarkably increased 1 to 10 days before the earthquake. This also analogous results for the different researches like Louis and Condell 2017. The effect of ionospheric disturbance is decreases on increasing the distance from the epicenter. This kinds of study provides new approach and opportunity to find out the possible seismo-ionospheric anomalies before the different earthquake. Acknowledgement. I would like to thank UGC for providing research grant to conduct the PhD research project. In addition, we are thankful to Gopi Simala for the TEC software and IMECO for providing the GPS-TEC data for all the stations. Furthermore, geomagnetic solar indices such as KP, solar flux, DX indices were derived from NASA OmniWave Data Explorer. So sincere thanks to team of NASA and UGC. Thank you, Association of Nepali physicists in America and Nepal Physical Society for providing opportunity to share my findings. These are my references, and thank you. I expect comments and suggestions. Thank you so much.
Thank you, Basu. So now we can take question.
I mean, this is very interesting.
Can we ask questions depending on the slide number? Can we go back, like on the second or third slide? Okay, here, yeah, that's the slide. Okay, yeah. So in this, like we have an image which shows ionosphere is disturbed by disturbances from above and below. My question is like, have you compared?
Yes, sir.
Have you compared how the differences? What are the differences between disturbances in the ionosphere from above, forcing from above, and forcing from below? Can you make any comment on that?
Thank you for the question, sir.
Can you make any comment on?
It's-
Okay, let me paraphrase the question. Okay, can you make any comment on the forcing on the ionosphere from above and below? Okay, because as the image shows, there can be forcing from magnetosphere as well, and there can be forcing from waves in the middle atmosphere as well. Both of them can disturb the ionosphere. So can you make any comment on what could be the nature, what could be the differences on those two forcings? Okay.
Thank you, Dev sir. Actually, the effect on the ionosphere due to magnetic storm is the ionizing process. जब म्याग्नेटोस्फियरबाट चाहिँ आयन्स म्याग्नेटिक फिल्ड आउँछ त्यसले न्युट्रल एटमोस्फियरलाई अथवा न्युट्रल एटमोस्फियरलाई त्यसलाई मोर आयोनाइज गरेर टोटल इलेक्ट्रोन कन्टेन्टहरू बढाउँछ that is the one way of fluctuating the total electron content in the ionosphere actually. But in lower atmosphereबाट जाँदाखेरि वेभ प्रोड्युस हुन्छ र त्यो वेभले नै टोटल एउटा इलेक्ट्रोन कन्टेन्टहरूलाई चाहिँ फ्लक्चुएट गराइदिन्छ. सो लोवर एटमोस्फियरबाट गएको वेभले आयोनोस्फियर टोटल आयोनोस्फियरलाई चाहिँ वी क्लाउड मुभ गरे जसरी मुभ गराइदिने हो. र म्याग्नेटोस्फियरबाट आएकोले चाहिँ त्यहाँ भएको अरू टोटल इलेक्ट्रोन मिन्स त्यहाँ भएको न्युट्रल एटम्सहरूलाई चाहिँ आयोनाइज गरेर टोटल इलेक्ट्रोन कन्टेन्ट बढाउने हो जस्तो लाग्छ एज माई थिङ्क. बट टिल नाउ आई डिडन्ट find out any types of the mechanical comments on that because I didn't do any research or I didn't do any research in that case, sir.
So that's fine. I think from the lower atmosphere, the wave activity may provide seed to disturbances. Okay, seed to hydrodynamic instability.
I mean, I don't agree with that point. Can you hear me, guys?
Yes. Why?
Okay. So basically, when you have a seismic wave, so those are like S and P wave, the primary wave, secondary wave, and surface wave. Those waves are like very, very low in intensity. I mean, if you see the intensity nature, those are very weak wave. So how is it possible that those waves propagate to the ionosphere and change the density in the electron?
Because they provide a seed. Because the ionosphere is a layer of this is my understanding, like high density fluid is stacked at a low density and a very small disturbance can also act as a seed to a larger hydrodynamic instability.
But again, remember, it has to.
This is really nice discussion topic. I think we are running out of time. I'm sorry to interrupt in the between, but we can do later on. Like we can discuss this later on. Let's move. Let's thanks Basu and move to our next topic. Next by Vogendra Katyal from Tribhuvan University, and his title of talk is Long-Term Atmospheric Visibility Variation in Two Cities of West Nepal from 1977 to 2020, a local proxy for local and regional atmospheric aerosol loads. So here we begin.
Namaskar. Very good morning, very good afternoon to all. I'm very glad to have you all here, although virtually. My name is Vogendra Katyal, a PhD scholar in Tribhuvan University, carrying out research work under supervision of Professor Dr. Dharan Prasad Sabaga and Dr. Anik Pandey. Today, I'm going to talk about my research work, long-term atmospheric visibility variation in two cities of West Nepal. Visibility is a very simple concept. It is the maximum distance at which a black object can be distinctly seen. It is a key observation in determining air pollution and status of optical properties of atmosphere. As seen in this picture, the seeing process depends on many factors like optical properties of illumination, the source itself, object being seen, intervening medium, and finally, the characteristics of observer. Degradation in visibility occurs mainly due to two basic reasons. They are met factors and air pollution factors. Among all met factors, humidity has very significant impact. Gases and aerosol components like sulfate, nitrate organic compound, black carbon, soil PM2.5, PM10, etc., whose size is comparable to wavelength of light, can change optical properties of atmosphere. In between these two factors, met factors have short-term effect, whereas air pollution has significant and long-term effect. Visibility is governed by very simple looking expression called cosmic meter. Formula is shown here, P equals to K by V, where K stands for cosmic meter constant and B for the extinction coefficient, which is fractional loss of light due to scattering or absorption per unit distance along the side path. It is total sum of scattering and absorption by gases and particles present in atmosphere. This sigma, which is function of position and scattering angle, is volume scattering function. This is ability of atmosphere to scatter light in given direction. This is sum of Rayleigh scattering and May scattering. Rayleigh scattering is basically by gaseous components present in atmosphere like nitrogen and oxygen. We can see Rayleigh scattering is highly dependent on wavelength of light, and this determines the basic color of sky. In other hand, May scattering is scattering by particles which are comparable in size with that of wavelength of light. It is combination of various phenomena like diffraction, refraction, phase shift, and absorption. In summary, visibility is an important indicator of atmosphere optics and used as proxy of air pollution studies. In my study, I have used historic climatological data of these two places, Surkhet and Bhairava. These two places have quite contrasting features in terms of geography and climatic condition. I have used very authentic, quality controlled historical data from NCDC. This data consists of two types of data. They have different standard of measurements, meter and SINO, and data is of 43 years period. Then, very rigorous data cleaning, data screening methods were used. Each screening method has its own significance. Two different approaches, computation of cumulative percentile and annual good bad days percentage were used to see long-term trend in visibility. The trend percentile here represents good days and 19th percentile represents bad days. We can see all the percentile level have decreased over the time period. Interestingly, in Surkhet, minor but temporary recovery in visibility condition is seen in period of 2000 to 2004 for our percentile levels. Whereas in Bhairava, the corresponding values are lower compared to Surkhet from the beginning. Steady decline in percentile values is seen throughout, and prominent decline is observed since mid-80s. The decline in visibility is less prominent in recent period because the values are already at low values. This method gives a general sense of degradation of visibility trend and the air quality in both places. To have better insight, we computed annual good and bad days percentage. If average daily visibility is greater than 15 kilometers, it is counted as good days. And if it is less than 5 kilometers, it is counted as the bad days. We can see for Surkhet, which are denoted by the pink lines. The complete for the good and the dash for the bad days. We can see simultaneous and sharp decrease in good days and increase in bad days have been observed in 2010. And we can see here, from the beginning, Surkhet exhibits relatively good general visibility condition. In contrast, the Bhairava has shown this process quite early in mid-80s. It is seen that good days are very less in the recent period for both the places. And regarding the bad days percentage, the Bhairava outnumbers Surkhet. This indicates that Surkhet has still good air quality condition. Here you can see notable monthly and seasonal variation of visibility and other met factors, humidity and temperature in both places. Monthly visibility in the two places so quite an opposite tendency. Surkhet shows highest visibility in November and the lowest in August, whereas Bhairava shows highest in July and lowest in Jan. Visibility record in Surkhet shows marked negative tendency association with humidity. This indicates that humidity is one of the major factors for degradation. And the monthly variation of humidity and temperature at both places show the similar pattern we can see here. You can see both places have best visibility condition in autumn season. Bhairava shows worst visibility condition during winter, whereas Surkhet shows worst visibility condition during summer. The corresponding seasonal average values of visibility are higher for Surkhet than Bhairava. This indicates better air quality in Surkhet. So with these results in discussion, we can draw the following conclusions. There is marked declining trend of air quality in both places. Overall air quality was better in Surkhet and still is. Degradation of air quality of Bhairava started quite early than Surkhet. There is a strong seasonal influence in air quality. Humidity has a prominent effect in Surkhet. Air quality degradation could be due to increase of various anthropogenic effects. A coordinated effort is required to mitigate the deterioration of air quality. Last but not the least, my sincere thanks and acknowledgement goes to following individuals and institutions for direct and indirect support in this research work. And thank you all.
Thank you, Bhogendraji. It was really nice talk looking at the seasons. Any question?
Yes, I would like to ask a question. Can we go to the conclusion slide?
Sure, sir.
First conclusion slide.
This one?
Yes. So the first conclusion is strong seasonality. No, I think there was one before this, right? Yes, one before this. Yes. Okay, the first one, visibility condition is relatively better in Surkhet than in Bhairava. But may I request the science? Like, will you please explain the science behind this conclusion?
Yes,
why?
Yeah, sure, sir. So here I have used the visibility factor as one of the proxy. It's not a direct measurement of the air pollution. Many researchers have used this method for the measurement of air pollution. So in terms of the visibility, seeing the visibility trend over the years, and I saw that is shown in the few graphs over there also. I saw the better visibility condition in the circuit than compared to Bhairava. That's why I drew this conclusion.
But my question is why? Why?
So because of it could be the presence of the air pollutants were more in Bhairava than in circuits. A correction and the other way.
Okay.
It might be it might also depend on the size of the particle as well. So
yes,
if your size of the particle is very close to the wavelength,
yes.
So basically that will attenuate more signal in compared to the larger particles. So the next question was, what was the size particles you used for your total extinction?
So the size is comparable to the wavelength of light, sir, but I'm not directly measured or directly used the air pollution data for this study.
Yeah, so basically I'm saying that, you have like so many range of dust particles, right?
Yes, sir.
That will take part in attenuation.
Yes, yes.
So did you choose any range of, the dust size, or did you like fixed like one particular type and then you calculate the extinction?
I have not calculated the extinction coefficient, sir. I have done the statistical analysis in this, seeing the visibility parameter only.
Right. Okay, it was a good work.
Yes,
Yeah.
thanks.
So much. Okay.
Yeah, so it was really nice session. A lot of information we have learned. So let's thanks all the speaker, and then we would like to say